Okay, so we are going to look at one of the discussion posted problems regarding the force that a muscle, the quadricep muscle, exerts on a leg when it is held at 30 degrees, and the force that the knee exerts on that same leg. So it says a person is sitting with one leg outstretched so that it makes an angle of 30 degrees with the horizontal, as my drawing indicates. The weight of the leg below the knee is 44.5 newtons with the center of gravity located below the knee joint. Now, we are going to make an assumption in this problem that this is the center of gravity and that it is a uniformly distributed leg so that the mass is acting at the end. And if this is 0.25 centimeters, or meters, excuse me, this is also 0.25 meters. So we are going to make that assumption in the problem. A 10-kilogram mass is resting at the top of the foot. The leg is being held in this position because of the force the muscle, the quadricep muscle, is applied, which is attached 10 centimeters below the knee joint, located, that's that 0.1. What is the force the quadricep muscle applies, and what is the force that the knee is exerting? All right, so two questions being asked. Now, this object, the knee, the leg, excuse me, the lower leg, is in static equilibrium. So it's not rotating, it's not translating. And we are interested in knowing the forces that are acting on that object. So that becomes our object of interest. All right. Now we can approach static equilibrium in two ways. We could do a force analysis, and all the forces in the horizontal and vertical directions have to be equal. And we can do a torque analysis where the net torque has to be 0. Which do we start with? Well, it's anyone's game, right? We can pick. If we pick the wrong one, we won't be able to solve it. We'll have to pick the other one. So let's start with the torque analysis. Now, with the torque analysis, we're going to draw an extended free body diagram. So here is my object that I'm interested in. I'm interested in that leg. So I'm going to draw that extended free body diagram. It's going to look like my picture because I'm not a very good drawer. I'm going to put all the forces acting on that object at the location that they're acting. So I know that the knee is exerting a force. In fact, it's one that I'm interested in. I don't know the direction. I know where it's located, right at this end. I don't know the direction that it's acting. But I do know that I can separate forces into horizontal and vertical components. So I could say that the knee has here's the force of the knee vertical, and here's the force of the knee horizontal. Now, why might I draw them in that direction? I'm making a guess, an educated guess. Maybe I'm really wrong, and it'll tell me. Based on kind of what I know about the problem. It's a guess. If, as soon as I calculate the forces acting on that object, the angle is going to come out in those forces. And so it'll tell me whether or not I have chosen correctly. All right. So those are my two forces. Let's look at then the next force. All right. Well, I have the force of gravity acting on the knee. It acts at the center of gravity. So that's the weight of my leg, and we're given that weight of 44.5 newtons. I also have this mass hanging out here at the end. That's pushing down on the foot, which is attached to the leg. So the foot's experiencing a force, and it too is experiencing that force of the weight of that mass. So that's mass times gravity of this mass. So that will be 98 newtons, 9.8 times 10. All right, and then of course I have the muscle itself. So the muscle inserts at 10 centimeters, and it is angled back in that direction. We're told that this angle is 25 degrees, and so it's acting at that location. All right, now to do a torque analysis, I have to define both the radii and the angles, which means I need to pick a pivot point. So we have to decide where to pick the pivot point. Well, typically I like to eliminate as much as I possibly can. I don't know anything about the forces being exerted by the knee itself, and so I'm going to put my pivot point there because that gets rid of those in my torque analysis. Once I have my pivot point there, then I can define my radii for each force. So for this force, we'll call this force 1. The radii is from the pivot point to where the force is acting. Here's radius 1. And then I extend that radius with my fingers, imaginary extension, and curl to the force. So there's theta 1. If this is force 2, Then my radius, this is one way to do it. Remember, there's multiple ways to do a torque analysis. Here's radius 2, and similarly, extend that radius in my head, and that becomes theta 2. For force number 3, well, we'll call the muscle force number 3. Here's my radius, R3, and I extend that radius. That becomes theta 3. And force 4 and force 5 will be my knee forces. And I can't draw a radius because they're at the pivot point. So now let's look at the torques and do a static equilibrium net torque equal to zero. Torque for force 1 is going to be the force times the radius times the sine of the angle. Well, my force is 44.5. My radius, well, I'm told it's 0.1 and an additional 0.5, so 0.25, times the sine of the angle. So what's the angle? Well, I know that this angle is 30 degrees. This is 30 degrees. There's lots of ways to figure out the angle. I like to be consistent, so I would say, well, that's a parallel line. That makes, if this is 30 degrees, that makes that 30 degrees. And if that's 30 degrees, that makes this 60 degrees. So it's in the negative direction, it's clockwise, so the sine of negative 60. All right, so we have 44.5 times 0.25 times the sine of negative 60. That gives us negative 9.634 Newton meters. Should it be negative? Yeah, it would rotate the object in the clockwise direction. Good. All right, torque number 2. Force 2, radius 2, sine of theta 2. Well, my force pushing down is the weight of that mass, so that's 98. It's acting at the end of the leg, and we said that the leg is cut in half, so that's 0.5. And similar to my analysis of this force, it too is acting at negative 60. So if you're not sure about that, go back and double check that analysis. All right, so we have 98 times 0.5 times the sine of negative 60. So we're left with negative 42.43 Newton meters. All right. Perfect. Should it be negative? Yeah, it's rotating it in the clockwise direction. Okay, force number 3. So the torque that force number 3 is exerting is the force times the radius times the sine of the angle. I don't know what that force is. We'll call it force M. I do know it's acting at 0.1 meters, and let's figure out the angle. Well, we know that this angle is 25 degrees. That makes this angle 155 degrees. So 0.1 times the sine of 155 is 0.042 times whatever that force is, times M. Should it be positive? Yeah, it would rotate that leg in the counterclockwise direction. All right, so force 4 and force 5, well, that's force 4, radius 4, sine theta 4. Well, the radius is 0, so that torque is 0. And force 5, radius 5, sine of theta 5, again, the radius is 0, so the torque is 0. All right, so I sum these up. We know that sum of the torques has to equal 0. So we have negative 9.634 minus 42.43 plus 0.042 M has to equal 0. Bring these two to the other side. We have 9.634 plus 42.43, or 44, divided by 0.042, and my muscle is exerting a force of 1239 newtons. All right, so I got the force that the muscle exerts. Check. How did I do that? Well, I did a torque analysis, looking at the forces acting on the object at the location they're acting, making sure I select a pivot point that's going to give me what I want, and then finding the radii, finding those angles, and using our torque relationship. Okay, that's part A. Part B asks us to find the force exerted by that kneecap. Well, the force exerted by the kneecap, that one is going to be a little difficult doing in a torque analysis because I don't have any idea what that force is. And I have two of them. So I'm going to end up with two unknowns. So we go to that other analysis. Now I'm going to have to erase this part, otherwise I will run out of room. So as we consider the translational equilibrium, so meaning it's not accelerating in a direction, we can do that force analysis that we've gotten so good at in our forces unit. Looking at a free body diagram, all of the forces that are acting on the object at the location they're acting, we're just going to take that extended free diagram and sandwich it down into into our regular free body diagram. So we're as if we're taking all this and collapsing it on its center of mass. So what forces are acting on it? Well, I have the force of gravity, which is 44.5. And I have the force of the block, which is bigger. Shouldn't draw it smaller if it's bigger. That's 44.5, which is 98 newtons. I have the force of the muscle. Well, if I were to sandwich this all down, that force of the muscle acts how? All right, this is where we get a little bit tricky. So this, if I bring this all the way to the center, all right, the force of the muscle is not 25 degrees off the horizontal. Here's the horizontal, okay? It's 25 degrees off of this 30 degrees. So what is the angle that that muscle is exerting? Well, it's 25 plus the 30. So if this is my coordinate system, it's actually acting at 55 degrees with respect to the horizontal. 55 degrees with respect to the horizontal. So imagine if this, here's my horizontal. That's 30 plus another 25. Okay, so we gotta be careful with those angles relative to the horizontal. All right, and then I have the force of the knee vertical and the force of the knee horizontal. And I'm just putting them in a way, and physics will tell us if we put them in the right direction. So those are all five forces acting on the object in a free body diagram. And like we've analyzed free body diagrams, we have, we'll number our forces. We'll number them the same way. And which was 4 and which was 5. I didn't even give them numbers. That'll be 4 and that'll be 5. And then we do our force separation. So we're going to separate into horizontal and vertical components. Force number 1 has nothing horizontal. It's acting down, so that's minus 44.5 newtons vertically. Force number 2, nothing horizontal. Acting down, negative 98 newtons vertically. Force number 3 has components. So we have, it's acting to the left, so minus m times, this angle is 55. So if I want to use that angle, it's the adjacent side cosine of 55. Right? I've already put in the direction because it was pointing to the left, and I'm using this interior angle. Right? So I've been explicit about that direction. If you were to use this angle of 125, you wouldn't need to put in that negative. The negative would come out. All right? So keep in mind those rules we talked about with angles and how you're using them. Vertically, it's pointing up, so that's going to be a positive times the sine of 55. So the opposite of that angle and the adjacent. All right? Force number 4 is my vertical force. So it's nothing horizontal, force of the knee vertical. And force number 5 is my horizontal force, nothing vertically. All right, so those are our forces acting. And again, if I drew them in the wrong direction, it's going to tell me. All right, so the sum of the forces horizontal is going to equal 0, and the sum of the forces vertical have to equal 0. All these forces have to sum horizontally and vertically to equal 0. So let's look at horizontal. Well, I have minus m times the cosine of 55 plus whatever the force is, horizontal, that has to equal 0. So I find that my horizontal force by my knee is equal to that should be an H, sorry, is equal to the muscle force, M, times the cosine of 55. And I erased our muscle force, so I have to cheat and look at the answer. That muscle force was 1239. So our force M was equal 1239 newtons. All right. So 1239 times the cosine of 55, our horizontal force is equal to 710.7 newtons. Okay, what about the vertical force? Well, we have minus 44.5 minus 98 plus m sine of 55 plus fk vertical. So these all have to equal 0. So my force of the knee vertical is, bring both of these to the other side, 44.5 plus 98, my book's in the way, plus, minus, got to bring that to the other side, the muscle times the sine of 55. So my force of the knee vertically, 44.5 plus 98, minus 1239 times the sine of 55 equals negative, it's telling me I drew it in the wrong direction, 872 newtons. So here are my components of the two force. I'm going to redraw it over here. My horizontal component is positive 710.7 newtons, and my vertical component is negative 872 newtons. So what is the force of the knee? Well, we have to use our Pythagorean theorem. So here's my total force of the knee. The magnitude of the force of the knee is going to be the square root of the horizontal and vertical components. We know this game. So 710 squared plus 872 squared. 72 squared equals square root that. The force of the knee is 1,124 newtons, and I just want to check that with it good, as it should be. I'm doing a little bit of rounding in the video, so your answer key is a little bit different. It's all about rounding. But I also need the angle. So can't forget the angle. The angle is going to be the inverse tangent of the y component over the x component. The inverse tangent of negative 872 divided by 710. Got to put in my parentheses. Gives us a negative 50.8 degrees. Now, is that the right angle? We always want to make that check. That's a common mistake. What quadrant does that angle tell me it's in? Fourth quadrant. Fourth quadrant has a positive x, a negative y, so I'm good. So that angle, we don't have to make an adjustment for the mathematics. All right. So to determine the force of the knee, I could examine my translational equilibrium. So separating the forces into vertical and horizontal components, smashing it all together at that center of mass, then just looking at the fact that it's not accelerating. Long problem, 2 parts, full analysis for both of them. Good job.